Welcome students to this lecture of the unit Chemical Bonding and Molecular Structure. In this lecture, we will discuss the following topics: ionic character in covalent compounds, percentage ionic character in covalent molecules and its calculation, covalent bonding and the characteristics of covalent compounds, valence bond theory for covalent molecules and its impact on structure and bonding. The bond formed between any two atoms is not a purely covalent bond. All bonding interactions have some ionic character because the electron density remains shared between the atoms. The degree of ionic versus covalent character of a bond is determined by the difference in electronegativity between the constituent atoms. The larger the difference, the more ionic the nature of the bond. Calculation of percentage ionic character and charge distribution. Based on Fajan's rules, it is expected that every covalent compound will have at least some amount of ionic character. The percentage of ionic character in a compound can be estimated from dipole moments. The bond dipole moment uses the idea of electric dipole moment to measure the polarity of a chemical bond within a molecule. It occurs whenever there is a separation of positive and negative charges. The bond dipole moment mu is given by mu is equal q into d, where q is the charge and d is the distance. A bond dipole is modeled as partial charge positive to partial charge negative with a distance d between the partial charges. It is a vector parallel to the bond axis and by convention points from minus to plus. Note that many texts appear to ignore the convention and point from plus to minus, which is totally wrong. The SI unit for an electric dipole moment is coulomb meter, that is cm. Typical dipole moments for simple diatomic molecules are in the range of 0 to 11 dBi. The percentage ionic character is numerically equal to observed dipole moment divided by the calculated dipole moment, assuming 100% ionic bond character. For example, for hydrogen iodide Hi, if the bond length is equal to 161 picometers and an observed dipole moment is equal to 0.44 dBi, then the percentage of ionic character can be calculated as mu percentage is equal to 1 into 1.602 into 10 to the power minus 19, which is the electronic charge, multiplied by 1.61 into 10 to the power minus 10, which is the distance, that is 161 picometers. It has to be divided by 3.336 into 10 to the power minus 30 for converting it into the dBi units. The total dipole moment comes out to be equal to 7.73 dBi, assuming 100% ionic character. The percentage ionic character thus will be 0.44 divided by 7.73 into 100, that is 5.7%. That means the percentage ionic character of hydrogen iodide molecule is 5.7%. Now let us discuss what actually a covalent bond is. Langmuir in 1919 AD proposed that when both the atoms taking part in chemical combination are short of electrons, then the nearest noble gas electronic configuration, they can share their electrons in order to complete their octets. Each atom contributes the same number of electrons to form common bond pairs which are then shared by both atoms. The bond formed by mutual sharing of electrons between two atoms so as to complete their octets or duplets in case of elements having only one shell is called a covalent bond. The number of electrons contributed by each atom is known as its covalence. For example, let us discuss the formation of chlorine molecule, that is Cl2. Each chlorine atom with the electronic configuration 287 has 7 electrons in its valence shell and needs one more electron to complete its octet. Both the chlorine atoms contribute 1 electron each to share 2 electrons. The bond can be represented by putting a line between atoms instead of bond pair. That's chlorine having 7 electrons in its outermost shell combines with another chlorine atom having 7 electrons in its outermost shell. Both the chlorine atoms share one pair of electrons and each gains an electronic configuration of 288, that is a stable nearest noble gas electronic configuration. Now, properties of covalent compounds. First, the state of existence. Covalent compounds exist as individual molecules. The intermolecular forces in these compounds are generally weak and hence exist as liquid or gaseous state. A few exist in solid state also. Now, non-conducting. Covalent compounds are generally bad conductors due to non-existence of ions. Covalent compounds have low melting and boiling points because the intermolecular forces between the molecules are very weak. Solubility. Covalent compounds are soluble in organic solvents and are insoluble in water and other polar solvents. Molecular reactions. The rates of molecular reactions are slow as the compounds involve breaking of covalent bonds in reacting molecules and formation of new bonds in the products. There are various approaches which explain the formation of covalent bonds. One of the earlier approaches is valence bond theory of covalent bond formation. The theory is also known as orbital concept of covalent bonding. The theory was put forward by Hitler and London in 1927 and was further developed by Pauling and Slater. The various postulates of the theory are: first, covalent bonds are formed by overlapping of half-filled atomic orbitals present in the valence shell of the atoms participating in bonding. Second, the orbitals undergoing overlapping must have electrons with opposite spin. Third, overlapping of atomic orbitals results in the decrease of energy and formation of covalent bond. Fourth, the strength of covalent bond depends upon the extent of overlapping. The greater the overlapping, more is the energy released and consequently stronger will be the covalent bond. The valence bond theory was proposed by Hitler and London to explain the formation of covalent bond quantitatively using quantum mechanics. Later on, Linus Pauling improved this theory by introducing the concept of hybridization. The main postulates of this modified theory are as follows. A covalent bond is formed by the overlapping of two half-filled valence atomic orbitals of two atoms which can be same or different. The electrons in the overlapping orbitals get paired and confined between the nuclei of two atoms. The electron density between two bonded atoms increases due to overlapping. This confers stability to the molecule. Greater the extent of overlapping, stronger is the bond formed. The direction of the covalent bond is along the region of overlapping of the atomic orbitals. That is, covalent bond is directional in nature. There are two types of covalent bonds based on the pattern of overlapping, which are discussed as sigma and pi bonds. The covalent bond formed due to overlapping of atomic orbitals along the internuclear axis is called sigma bond. It is stronger bond and cylindrically symmetrical. The electron density is in between the two atoms in a sigma bond. Depending on the type of orbitals overlapping, the sigma bond is divided into different types. If the overlapping takes place between an s and another s orbital, the sigma bond formed is called sigma ss bond. If the sigma bond is formed by the head-on overlapping of two p orbitals, the sigma bond is called sigma pp bond. Similarly, if the head-on overlapping takes place between an s orbital and a p orbital, the sigma bond formed is called a sigma sp bond. There are various other types also. Now, the pi bond. The covalent bond formed by sideways overlapping of atomic orbitals is called a pi bond. In this bond, the electron density is present above and below the internuclear axis. It is relatively a weaker bond since the electrons are not strongly attracted by the nuclei of bonding atoms. The electron density lies above and below the atoms in a pi bond. Pi bonds are weaker than sigma bonds since there is less overlap. Thus, two single bonds are stronger than a double bond, and more energy is needed to break two single bonds than a single double bond. Thus, s orbitals can form only sigma bonds, whereas the p, d and f orbitals can form both sigma and pi bonds depending on the pattern of overlapping. Now, bonding in different molecules as explained by valence bond theory. First, let us take the example of hydrogen molecule. The electronic configuration of hydrogen atom in the ground state is 1s1. In the formation of a hydrogen molecule, two half-filled 1s orbitals of hydrogen atom overlap along the internuclear axes and thus form a sigma ss bond. Chlorine molecule. The electronic configuration of chlorine atom in the ground state is neon 3s2, 3px2, 3py2, 3pz1. The two half-filled 3pz atomic orbitals of two chlorine atoms overlap along the internuclear axis and thus form a sigma pp bond. Hydrogen chloride molecule. In the ground state, the electronic configuration of hydrogen atom is 1s1 and the ground state electronic configuration of chlorine atom is neon 3s2, 3px2, 3py2, 3pz1. The half-filled 1s orbital of hydrogen overlaps with the half-filled 3pz atomic orbital of chlorine atom along the internuclear axis to form a sigma sp bond. Now, the oxygen molecule, O2 molecule. The electronic configuration of oxygen in the ground state is helium 2s2, 2px2, 2py1 and 2pz1. The half-filled 2py orbitals of two oxygen atoms overlap along the internuclear axis and form sigma pp bond. The remaining half-filled 2pz orbitals overlap laterally to form a pi pp bond. Thus, a double bond, one sigma pp and one pi pp is formed between two oxygen atoms. Now, the nitrogen molecule. The ground state electronic configuration of nitrogen is helium 2s2, 2px1, 2py1 and 2pz1. A sigma pp bond is formed between two nitrogen atoms due to overlapping of half-filled 2px atomic orbitals along the internuclear axis. The remaining half-filled 2py and 2pz orbitals form two pi pp bonds due to lateral overlapping. Thus, a triple bond 1 sigma and 2 pi is formed between two nitrogen atoms. Now, there is a need for modification of valence bond theory. because the old version of valence bond theory is limited to diatomic molecules only. It could not explain the structures and bond angles of molecules with more than 3 atoms. For example, it could not explain the structure and bond angles of water, ammonia, methane, etc. In order to explain the structures and bond angles of molecules, Linus Pauling modified the valence bond theory using the hybridization concept. Dear students, this was all about today's lecture. Hope you have understood it well. Thank you.